Hello, chemists. This is Jolly. These are the examples that I gave you. They include the proton NMR, the carbon-13 NMR, the IR, and the mass spec. And we're going to work through them. I'm just going to show you how I would approach it. And because I have 4 spectra, I'm going to glean as much information as I can from each spectra before going back. Now remember, there's lots of problems individually for carbon-13, proton, IR, and I highly suggest you do each of those first before you're trying to put them together. And then I will also put a PDF with all of these worked out in their gory detail under the reference for Moodle for you. All right, so here is question number 1. Now, the key to this one is, let me actually get to the correct screen. All right, the key to this one is determining what functional group you're in, or what spectra that we're actually in. And so the x-axis goes from 0 to 10, and it's in ppms, and that is either the carbon-13 or the proton NMR, and because it goes from 0 to 10, this has to be the proton NMR. We also know that because they're splitting in these peaks, okay, and the carbon-13 doesn't split. All right, now the first thing you should do is label how many peaks you have, and I tend to use lowercase letters, so A, B, and C. So there are 3 peaks, which means there are 3 unique types of hydrogens. So I usually make a little note to myself right here in the top corner. There's 3 peaks, which means there's 3 unique types of hydrogens. And then I count how many they integrate for. 3, 4, 5, 6. So there's 6 hydrogens. And remember, even numbers of hydrogens mean there are no halogens and no nitrogen. So already I know a lot of information from there. The next thing I'm going to do is I'm going to determine what the splitting and the location or the chemical shift. All right, so down here, beware the shadow peak. This right here is not a splitting. Okay, that is the shadow peak. They can be very confusing, but this is really a singlet that integrates for 1. And it is about, I don't know, 9.8. All right, this one is around 2.4. Now, if you'll notice the symmetry, this is kind of squished together, but the symmetry kind of looks like this. And with experience, you'll start to recognize that. So I believe this one is a quartet that integrates for 2, and it's around 2.4 ppm. Now, again, there's shadow peaks. Do you see these dark things? But there's a peak on the left and a peak on the right that are almost the same height. So I believe this is a triplet that integrates for 3, and it is around 1.1. Now, you definitely want to leave some space on your spectra, but I like to keep everything like lumped together. So I'm going to go up here and I'm going to say A is a singlet, which integrates for 1, which is around 9.8. Now, I'm going to not write ppm each time, but if you're doing this on a report or anything official, make sure you still put the unit. All right, B is a quartet for 2 hydrogens at about 2.4. And then I have a triplet for, back. For C, I have a triplet that integrates for 3 at about 1.1. All right, that's what I know. Now I'm going to interpret. Okay, now I'm going to interpret. What does a singlet for 1 hydrogen around 9.8 mean? Generally, that is the aldehyde region. So I believe I have an aldehyde right there. All right, what could a quartet that integrates for 2 mean? Now keep in mind, this is a ballpark, but it works most of the time. If it integrates for 2 hydrogens, it's more than likely a CH2. If it integrates for 3 hydrogens, it's most likely a CH3. Beware of symmetry, though. Beware of symmetry. But because it's integrating for 2, I believe that is what I'm talking about. And in order to get a triplet, one possibility is that. In order to get a quartet, one possibility is that. All right, and it is somewhere between 2 and 2.5. So this also has to be connected to, I already know I have a carbonyl, but it has to be next to something, okay? to make it shift. And that is the perfect thing because I already know there's an aldehyde. All right, and then how am I going to get a triplet for 3? So again, CH3 is the most logical. And in order to make a triplet, it has to be connected to a CH2. Now, normally, that's the information I have, and I would move on. But right now, if anything is like jumping at you, or if it's saying you can put it together, it's okay to put a structure together right now. And this one's fairly simple. All right, so there's the 3 pieces all put together. If you ever come up with a structure, make sure you check the end. So first of all, I know there's supposed to be 6 hydrogens, so 3, 4, 5, 6. That's fine. Then I need to go and I'm going to predict, if you will, backwards to make sure. So this one, I would expect, I'm hiding the CH3, and so I'm expecting a triplet that integrates for 3, and it is just an alkane, a little bit shifted, so maybe somewhere between 0 and 2. This one has I'm hiding the CH2, 1, 2, 3. These do not split. Okay, aldehyde hydrogens don't participate in splitting. So I'm hiding the CH2, so 1, 2, 3 plus itself. That's going to be a quartet that integrates for 2. And the beautiful shift for carbonyls is somewhere between 2 and 3. And then I should have a singlet that integrates for 1 hydrogen somewhere between 9 and 11. And then I double check. Did it do exactly what I expected? And the answer is yes. And then I need to say who's responsible for each peak. So this is responsible for A. This is responsible for B. And that one is responsible for C. Now we actually answered the whole problem using just the proton NMR, but sometimes it's not that easy. So let's go to the carbon 13. How are we going to know it's a carbon 13? Because it's in ppms and it's going all the way from 0 to 200. All right, so I'm going to do the same thing. I'm going to count how many peaks. Now either label this with a capital A or a number 1, just so they're not identical and they don't get confused. There is no splitting. Okay, there's no splitting in the carbon 13. This right here is the shadow peak. Beware the shadow peak. Okay, don't count that as 2 peaks. So there are 3 peaks in this spectra, which means there are 3 unique carbons. And now let's look at those numbers and see if we can glean any information. Now anything in this region is a carbonyl, so there's a proof that I have a carbonyl. And then pretty much anything down here is just your sp3s. And we know that B is further shifted than C. All right, that didn't tell us much. But I do know the structure already because I came up with it with the proton. We're going to do the same thing. We're going to draw it on here, and then we're going to say who is responsible for which peak. So A is responsible for that. B is further downfield, so it must be close to that electronegative group or that withdrawing group. And then C. And then C. All right. Oh, how are we going to know this is a IR? Well, I hope wave number, and I hope just the overall shape screams at you. All right, now remember on IRs, you need to draw a line around 2800. Okay, that was a bad line. And then around 1900. And then again at 1500. As you get more experienced, you won't have to draw those in. But remember, this is the hydrogen world. This is the carbon triple bond world. This is the carbon double world. And the only time we look in the fingerprint is for extra or secondary proof. All right, we have to look at shape and intensity. So at 2900, we always have this oven mitt shape. That is your sp3 hybridized carbons. Now these two are not attached, and that is around 27, 28, and that screams at me CHO. But I can't have a CHO, I can't have an aldehyde unless I have what? So that takes my eyes right there. That is your carbonyl peak, a very strong peak between, 16 and 1800, usually around 1700. All right, and then is there anything in this fingerprint that is, really jumping up and down? Not right to me. Now this peak right here is noteworthy, okay? I don't really know what it could be. Is it harmonics? But it is noteworthy. So that one, and remember, anytime you have a carbonyl, this is the harmonic peak or overtone. And that, again, in this one, I know it's not anything, but if you were looking at this and nothing else, you would have to say, huh, I wonder if that's, okay? All right, and so what functional group do I think I have on here? It looks like an aldehyde. Now, of course, we just did the carbon 13 and the proton, so we know that's true, but based only on what I'm looking right there, it looks like an aldehyde. All right, how are you going to know this is a mass spec? Because M to Z is mass to charge ratio is on the x-axis, and the intensity is on the y. Remember, the absolute tallest peak is called the base peak. But we're looking for the molecular ion peak, so you go all the way to the right. Now, I'm not quite sure. Do you see there's a little hiccup there, hiccup there, hiccup there, and hiccup there? Those could be the molecular ion peak, but they're so small they could also be background. So I'm going to go for this one. Okay, it's the most dominant peak furthest to the right. And then I always go one back, and I look for the relationship. So this is the M, okay, this is the ion, and this is the M plus 1. Because remember, the M plus 1 is the carbon 13, and it should always be much smaller, okay, much smaller than the molecular ion. If you go two back, do you see this peak and this peak? It's not in the ratio of big to small. Okay, so the molecular ion and the M plus 1 always have to be big to small, and that doesn't fit. So this is not your molecular ion. So I made a pretty good guess right there. Now in this case, I did tell it to you, but let's just double check. So 55, 56, 57, and 58. So my molecular weight, always write your molecular weight on your spectra. Label your molecular ion and M plus 1 and M plus 2. And then let's do some interpretation. I have an even molecular weight, so I know there are no nitrogens. There is not an M plus 2 peak that is relevant, so I know I do not have a halogen, specifically chlorine and bromine. And then I can just work backwards. This spectra does not tell me anything about oxygens, so I'm just going to have to use some math skills now. All right, so I have 58 AMU, and I know from the above picture that I have at least one oxygen. So I'm going to subtract one oxygen, and that's going to leave me 12, that's going to leave me 32, and how, did I do that right? 8 minus 6 is 2, 5 minus 3, of course I didn't do that right, it's a 4. Alright, so 5 minus 1 is 4. Alright, so how many carbons, how many 12s will go in there? That looks like about 3 carbons. So I'm going to subtract 36, and 12 is 6, and so that leaves me the number of hydrogens. So I believe my formula is C3H6O. Now I'm going to check it. I'm going to use units of unsaturation and check and see if that's even a possibility. So 2 times 3 plus 2. So 6, 7, 8 is the total hydrogens possible. I only have 6, which is a difference of 2. And remember, hydrogens always come off in pairs, so you divide that by 2. And that is telling me there's 1 unit of unsaturation, which means there is 1 ring or 1 pi bond. And I already know there's a pi bond, so this perfectly matches. All right, before I move on, I go back and make sure that everything jives. So C3H6O with 1 pi bond. All right, now the C3H6 isn't going to help here, but there definitely is 1 pi bond, and it's part of that carbonyl. Up here, a carbonyl shows up around the 200 range, okay, so it's jiving. And then go all the way back to the proton NMR, C3H6O. I have the indications of an aldehyde, 1, 2, 3, 4, 5, and 6. There were 6 hydrogens. All right, everything is looking good. So when you're finished, you're going to have everything labeled, your interpretation, and then your final structure labeled with the peaks belonging to whom so the A, B, and C labeled where they're supposed to be. Same thing on the carbon-13, okay? That's how you would label the IR, and that is how you would label the mass spec. Now remember all my individual handouts. If you didn't get part of that, if you go to each of the individual handouts for the spectra, it'll teach you all of the details for each one of those. All right, there's question 1, and I will be doing all 8 questions, but I'll do them in individual videos. And so until the next one, Jolly out.